In part 2 of our lesson on the inverse circular functions, we will study the inverse sine function. To begin with, let's take a look at the graph of y equals sine of x. Now, it's pretty easy to see that this is not one-to-one because it fails the horizontal line test. In fact, it'll fail it infinitely many times because a horizontal line passing through the sine curve will intersect it infinitely many times. Now, in our algebra review, we learned that in order to make this graph one-to-one, we will need to restrict the domain. So let's think about which x values we should choose so that the graph will pass the horizontal line test and yet still yield every possible y value in the range. Now, when we look at this graph, we see that the range goes from -1 all the way up to +1. So the piece of the graph that we choose has to include all of those y values. Now, because the graph of sine goes infinitely in the positive x direction and infinitely in the negative x direction, we have infinitely many sections of the graph that we could choose. It's common to choose the section of the graph closest to the origin that you possibly can that will still give you every y value on the graph. So the standard is to choose from -π/2 up to +π/2. We pick that section of the graph to use because, as you can see, we will get every possible y value from -1 to +1. And now when we pass a horizontal line through the graph, it will only intersect that red section of the graph in one point at a time. So now this function will be one-to-one in the restricted domain. So we're going to restrict the domain to be that x has to be between -π/2 and +π/2. To help us create the graph of the inverse sine function, let's name some points on this section of the graph that we're using. We know that this point right here has the coordinates -π/2, -1. Also, an easy point to name here is -π/6, -½ Here we have 0, 0. Here we have π/6, 1/2. And finally here we have π/2, 1. What we'll do next is use these 5 points to create the graph of inverse sine function by using the definition of inverse function, which says we'll take these x and y values and switch them. Now on our sine graph, we had the point -π/2, -1. So that means it's going to become the point -1, -π/2. We take the point from the sine graph of -π/6, -½ and on inverse sine, that point will be -½ -π/6. 0, 0 will still be 0, 0 when we switch x and y. From the sine graph, we have the point pi over 6 1/2, so it's going to become 1/2 pi over 6 on inverse sine. And finally, from the sine graph, the point pi over 2 1 becomes 1 pi over 2 on the inverse sine graph. And here's the shape of this graph. See how the curves go in the opposite direction from sine of x because of the reflection over the line y equals x. Now, something to notice is that this is the complete graph of y equals sine inverse of x. Unlike the sine function, this function does not go on and on forever and ever and ever. It's not periodic. This is its entire life cycle. So then let's figure out the domain here. Remember that domain is all the x values. So in this case, the x values start at -1 and go up to +1. So the domain is -1 to 1. The range of y equals sine inverse of x is all the y values that result. And we can see, looking at the graph, that the smallest y value we will ever get is -pi over 2, and the biggest y value we will ever get is +pi over 2. So the range is -pi over 2 to +pi over 2. So just a reminder that this is a big difference from the trig functions. Sine of x goes on forever and ever, and it is not a one-to-one function. Sine inverse of x does not go on forever and ever. Remember, this is its entire life cycle. It is a one-to-one function. Now, when you're looking at the graph, you know that a one-to-one function passes the vertical line test and the horizontal line test. And be reminded that another way to think of a one-to-one function is that every x value has exactly one y value, and every y value has exactly one x value. So that's another way to think of one-to-one functions. So a one-to-one function means each x value has only one y value and the other way around. And each y value has only one x value. So if you input a value, it can only output exactly one unique value. There will be no two input values that give you the same output value. And that's very different than sine. For example, with sine of x, we can input pi over 6 and it outputs a half. We could also input 5 pi over 6 and it would output a half. That will never happen with inverse sine. If we input a value, it only has one possible output value. Now, to help you understand that a little better, you can think of sine and inverse sine like machines. Let's start off with the machine called sine. Now, we know that we will input its domain. And in this case, let's talk about the restricted domain so that we're talking about the one-to-one version of sine. And remember, on the graph, we said we're going to input angles from negative pi over 2 to positive pi over 2. And then the machine called sine will output its range, which is real numbers from -1 to +1. Now remember what happens from a function to an inverse function. We switch x and y. So then that means the inverse sine, when we input its domain, that means we have to input real numbers from -1 to +1, and that means it's going to output a range of angles from -pi over 2 to +pi over 2. Remember, we talked about this with inverse functions and functions. The domain of the function becomes the range of the inverse function, and the range of the function becomes the domain of the inverse function. So what inverse sine outputs are angles. And that's a big difference. With the function sine, we would input angles and it would output real numbers. Well, for inverse sine, we have to do exactly the opposite. We're going to input real numbers between -1 and 1, and it's going to output angles. And those angles can only live from -pi over 2 to +pi over 2. If theta is the output of sine inverse of x, right? Make sure you take that in now. Sine inverse of x, remember what's going in here. Real numbers are going in from -1 to 1. That's what's going to go in for the x value. Then that means what the function will output is an angle between -pi over 2 and +pi over 2. Now, if you look at this equation, we know that we could undo the inverse function by taking the sine of both sides. So if we have theta equals sine inverse of x, then that will mean sine of theta has to equal x. And you will see in a minute how we use this concept to help us find exact values of inverse trig functions. Now, just a quick note here that an alternate notation for sine inverse of x is arcsine of x, and we will use both of them throughout the semester, and when you get to your calculus class, you will use both notations. We are ready now to try this example where we have to give each exact value. In this first one, we have to evaluate the sine inverse of 1/2. Now remember, the output of sine inverse of x is an angle. So that means this thing is an angle, and we can rewrite this in this form. That means saying that theta equals sine inverse of 1/2, that's this form, is equivalent to saying that the sine of theta is equal to 1/2. Now remember, a very important limitation is that theta has to be from negative pi over 2 to positive pi over 2. So what you're doing right now is thinking your way through this and saying, which angle from negative pi over 2 to positive pi over 2 would it be true that sine of that angle is equal to 1/2? Well, the only angle for which that is true is pi over 6. So the sine inverse of 1/2 is pi over 6. It is the only answer that you could ever give. Now let's take a minute and relate this to our graph of inverse sine that we made. You can see if we input a value of 1/2, then the sine inverse function will output one and only one value, and that is pi over 6. Let's try this next one where we have to evaluate the sine inverse of negative 1/2. Once again, remember that the output of sine inverse is some angle. So if we let theta be the angle that is the output of sine inverse of negative 1/2, and we rewrite it in this form, then that means that the sine of theta has to equal negative 1/2, and we know that theta has to be between negative pi over 2 and positive pi over 2. Well, the only angle in this interval where it would be true that the sine of that angle is negative 1/2 is negative pi over 6. Relating this to our graph of inverse tangent, we see that if we input a negative 1/2, then the function is going to output one and only one value, and that is negative pi over 6. Now here, we know that the output of the sine inverse function is going to be an angle, and when we write it in its equivalent form, we know that means we can think of it as sine of theta has to equal 1, and we know that theta has to be between negative pi over 2 and positive pi over 2. The only angle in this interval for whom the sine of that angle is equal to 1 is pi over 2. And once again, relating to the graph of sine inverse, we can see if we input a value of 1, it's going to output one and only one value, and that is pi over 2. Here, once again, we know that the output of an inverse sine function is going to be an angle, and writing it in the equivalent form, we know that means we can write it as sine of theta has to equal negative radical 3 over 2, and we know that theta has to live from negative pi over 2 to positive pi over 2. Now, given that theta has to be in this interval, we know that the only angle for whom the sine of that angle would be negative root 3 over 2 is negative pi over 3. If we take a look at the graph of sine inverse, and we have an input value of negative root 3 over 2, you can see that the function is going to output a value of negative pi over 3. So that is the one and only value it could output.